Hi, I'm Billy Woodford. I'm co-founder and CTO here at Form Energy. Today we're at our lab in Somerville, Massachusetts, and we're going to take you inside and show you around. Come on in with me. What you see here is about 45,000 square feet of light industrial space that we built out to our specifications to do this kind of next-generation battery technology development work. We're going to start with looking at small batteries that we used in the early days to select iron air, and the test articles that we used to develop iron air batteries and make decisions about what does the actual product look like. We started the company in 2017. Throughout that year in the laboratory here in Somerville, the technical team got to work on testing things, and at the end of 2018 is really when we selected iron air for our first product. Today we operate in 3 sites. Here in Somerville, Massachusetts is really where we do our R&D work. In Berkeley, California is our engineering site, and there we take a single iron air battery cell and develop all of the things that are needed to turn that into a power plant. That then hands off to our site in the Pittsburgh, Pennsylvania area, where we're today doing pilot manufacturing, learning how to make all of those components on a continuous basis that we can deploy in the next facility that we'll have, which is a high volume manufacturing site. So first I want to tell you about what an iron air battery is and how it works. And to do that, I'm going to use some of the pieces, the components of one of our subscale, sort of miniature size batteries. This is an iron electrode, and this is an air electrode. And those are the 2 main components of an iron air battery. When the battery is fully charged, these electrodes face each other and submerged everywhere around this liquid electrolyte. The air electrode breathes oxygen from the air into the battery, and that makes ions that migrate over to the negative electrode, where this iron is rusted. It's turned from iron metal into iron oxide. That's what releases energy. To recharge that, to store energy, we force electrons into the iron electrode and drive it from iron oxide back to iron metal, and that's the derusting process. Ions move back across the liquid electrolyte to the air electrode, where they are converted back into oxygen bubbles that fizz out of the cell. And so when we look at one of our large cells, you see bubbles rising up out of the liquid electrolyte. And so that's just the basic ideas of how an iron air battery works and what we mean in a little bit more detail when we say it works by reversible rusting and derusting. Safety was a key consideration in our technology selection, and it's really been a focus as we've been developing and designing our iron air battery system. Through a California Energy Commission grant, we've been collaborating with EPRI and others really to conduct first a code and standard review, and then to develop third-party testing plans for the safety and abuse testing and verification of our product and system. Iron air is the lowest cost rechargeable battery chemistry. It's safe, it is non-flammable, the iron materials are non-toxic. Iron electrodes can be made to be very durable and to be long-lived. It is scalable, it's not reliant on anything very rare, expensive, difficult to source or scale. When we were really deciding what is the right technology, we were asking what kind of iron material to use and how to turn it into an actual battery electrode. This material is called direct reduced iron, and it is the lowest cost form of metallic iron produced on the planet. It's used in electric arc furnace steelmaking exclusively. We were the first to realize that it could be used in a battery. One of the key things is that it's porous, and that's beneficial for the performance of the battery. Like a sponge, they can absorb a lot of liquid electrolyte inside of them. That helps ions get around, and it helps the battery just cycle back and forth. And we don't have to do anything special to create that porosity. It's just made that way. And so our first tests with direct reduced iron were with these little beaker cells in which we were testing single individual marbles. We tested dozens and then hundreds of these little batteries in beaker cells to show that you could efficiently get energy in and energy out multiple times. And that really is what enabled us to select a 100-hour iron air battery as the technology for our first product. We can make iron air batteries across really any duration. So why 100 hours? The answer for that really comes from our analytics work and the software tool that our team has built, Formware. We can model whole portfolios, we can model individual projects, and across really a wide range of use cases in different geographies, different resource mixes, we find that a 100-hour product is the one where we can really deliver the most value for our customers as we develop this new multi-day storage system. Since then, we've been working on scaling that up, showing that groups of pellets can work together, and then defining exactly what size groups of pellets have to work together in order to enable a utility scale product. And what you see represented on this bench is in some ways the history of that journey, from those single pellets to a block of those pellets all sandwiched together. And then we learned that to actually make the pellets work together, you needed to crush them up and to put them back together again to form very strong metallurgical bonds between the individual pieces. And that's how we make these kinds of electrodes, is we take those pellets, we crush them down to a powder, and we put them back together again. In addition to defining how to make that iron electrode, what materials to use, we had to define how big to make it. And that's one of the key questions that we had to answer, is how to go from this basket of iron material into an actual product design. And what we've ended up with is iron electrodes and air electrodes that are 1 meter tall and 30 centimeters wide. And then many, many hundreds and thousands of these electrodes will comprise a power plant. So the battery testing that we do today, we really do at 2 different size scales. We do things that are full scale. We also do subscale testing, really in order to understand the materials, the chemistry and electrochemistry questions inside the heart of that iron air battery. And to do that, we use cells that are in these Tupperware containers. This is a single iron air battery cell, and we can use different iron materials, we can use different electrolytes, and in Somerville, we've built up the capacity to do many, many of these tests in parallel. And we have dozens of test stands for testing the full-scale cells. So we're gonna go see first is our full-scale development area and talk a little bit more about the actual full-scale design and the testing that we do there. Then we're gonna go see the subscale test area and see those small iron air batteries on test. So what we're gonna see now are some of our full-scale cells getting ready to go on test. This is our milk jug kind of material, and inside of that are our iron electrodes and our air electrodes. And so this cell is the building block for power plants of iron air batteries. This is the largest thing that we test here in Massachusetts, and it's the smallest thing that we test at our site in California. And so what we're doing here is preparing to do testing of individual cells to really understand at this level the performance and the design of the cell. And what you're gonna see next are these cells and earlier generations of these cells doing testing. So this is our full-scale cell test lab. And what you see to my left are the first dozen of those cells that are on test here in Massachusetts. The 2 cells you see most immediately beside me are on the right-hand side an earlier generation design to define the size scale. So why is the cell a meter tall? Why is it 60 centimeters wide? Why are there 2 electrodes that go inside of it side by side? All of those kinds of decisions. And then to its left is the actual production intent design. The learnings that we get here with those cells help to inform the performance of that battery and how to drive it up over time. In parallel, in Pittsburgh, Pennsylvania, we're learning about the manufacturability of that design and how to further improve it to make it really easy to make millions of those cells as we really ramp to very high volumes of production.
We're really excited. We just announced that we'll have a high-volume manufacturing site in Weirton, West Virginia. We selected the site in Weirton, West Virginia after a months-long and nationwide site selection process. We focused on some of the key logistics requirements for manufacturing an iron air battery. We have to move at scale lots of iron material that is not lightweight to move around. And so access to logistics such as rail and water are really key components of the site selection process. And ultimately selected to work in Weirton, West Virginia because there's a really talented workforce that understands how to do industrial processes and how to manipulate iron into products. And West Virginia also has a very pro-business climate that's really conducive to us. This is a major milestone for us as it represents the site where we'll be ramping up very substantially over the coming years.
The next thing that we're gonna go see are our subscale tests. Each one of these Tupperware containers has a single subscale iron air battery cell inside of it. Inside of this temperature-controlled chamber, there are about 50 of those batteries, so we have dozens of these temperature-controlled chambers around the lab. Each one is set at a different temperature, and so we're able to learn about performance across a wide range of temperatures. Each cell has a different iron material a different electrolyte, a different air cathode, or it's doing a different kind of cycling to simulate a different use case with a different geography or a different mix of solar or wind or different weather profile. So we can learn a lot about how iron air batteries perform and how to optimize the performance and the design of the full-scale cells while being able to iterate much more quickly on the chemistry and materials questions. What we're gonna go see next is our wet lab, where every one of these cells, after it's completed its testing, we take it at its end of life, dissecting it to understand at a very detailed level what happens inside of these iron air batteries. The wet lab is a great last stop for our lab tour, and there's really 3 different categories of things that we do inside of this lab space. The first is the development of our liquid electrolyte. We're really focused on the development of additives, things that we add in small amounts that really modify the performance of the battery very significantly. Another is after we've done the electrochemical testing of a battery, we tear it apart and dissect it and understand at a very detailed molecular or atomic level what has changed and really inform the next set of materials to test. The final thing that we do in here is the development of next generation battery technologies. Iron Air is of course our first product, but we have other ideas for new battery chemistries and new product designs. And this is where we start that very earliest stage development work, and it's really where we close the cycle of learning on the subscale testing that we do in this site.
Form Energy has 2 announced commercial partnerships right now. Our first customer is Great River Energy in Minnesota. That'll be our first customer-facing grid-connected system. We're also in discussion with Georgia Power about deploying into their system. We have a number of other commercial negotiations right now.
I'm John Brecky. I'm Vice President and Chief Power Supply Officer with Great River Energy. Great River Energy is transitioning to a mostly renewable energy portfolio. We saw the need for low-cost, long-duration energy storage, and we were aligned with Form Energy in that vision. We have extreme weather here in Minnesota, and our members expect reliable energy at all times. Long-duration storage has the potential to keep the electric system balanced and reliable in times of shortages and need that can last for many hours or days. These resources can also provide an energy hedge against price volatility in the market. We believe the benefits of long-duration storage will only increase as renewable energy grows over time. These resources will be the key to unlocking the value of wind and solar in the market while maintaining reliability and affordability.
Well, thanks for joining us on our virtual lab tour. It's been great to show you around our site in Somerville, Massachusetts, as well as to show you a little bit about our other sites. We look forward to staying in touch. Thank you.